Moving right along, we have lots of basic differentiation types that we know. So we're going to hit right into the basic integration rules as well. So we already knew that the derivative of, I'll start with this one, the derivative of sine is cosine. So the derivative of cosine is going to spit you back out to sine. Should make sense. We knew that the derivative of cosine was negative sine. So that means that the antiderivative of sine will be negative cosine. Again, the derivative of tangent was secant squared, so the antiderivative of secant squared is going to be tangent. You can see that these all come from those basic differentiation rules. We have a few basic trigonometric integration rules. Notice that we do not yet have one for integrating tangent. That's not on my list because tangent wasn't what was spit out as a derivative in any of my trigonometric functions. Just sine, cosine, secant squared, and some combinations, some products. So I can integrate the product of secant and tangent without having to use some kind of product rule because I know that its derivative is going to be just secant because, sorry, its antiderivative is going to be secant because secant's derivative is the product secant times tangent. Okay, so we want to keep these in mind, the relationship between the derivatives and the antiderivatives, because it allows us to jump backwards and forwards between them. In part A, we have a constant multiple, 3 times sine of x, and so that's going to integrate into 3 times the integral, or antiderivative, of sine of x, which is negative cosine of x, plus c. And so that simplifies just to negative 3 cosine of x plus c. I know that 5 is a constant multiple, so the antiderivative or integral of 5 secant squared of x will be 5 times tangent of x plus c. We're not concerned with where we put the 5. It does not need to be in parentheses around the c because that c is arbitrary. So 5 tangent of x plus c. Okay, now in part C, I don't have a quotient in one of my patterns, so that's not something I can currently separate. However, I am going to be able to use some trigonometric identities to rewrite this. So let's start by distributing that denominator. So this is the same as the antiderivative of sine theta over cosine squared theta minus 1 over cosine squared theta d theta. And then even though I usually, for trig, want things in terms of sine and cosine, that's not necessarily true here. So we're going to get these into their reciprocal functions. So 1 over cosine squared, that is secant squared. And then that's something I want, right? Because I know how to integrate secant squared with number 14. Now I need to rewrite this one. And so I might want to separate this as first sine over cosine times cosine. And so I'm really thinking about this as being sine times 1 over cosine times cosine for the cosine squared. So I can get that separated into sine over cosine, which is tangent theta, and then 1 over cosine, which is secant theta, minus the secant squared theta. Because with rule 16, I can integrate the product of tangent and secant. So I need to get this rewritten into a form that I can do the antiderivative or the integral of. So the antiderivative of tangent times secant, or secant times tangent, is secant of theta. And the antiderivative of secant squared is tangent plus c. Now, again, I don't know if you're wondering this or not, just want to mention it. Technically, I integrate these two things separately, so they each generate their own c, but those two c's are just combined into this one arbitrary c. So just one c for the whole thing, please. Okay, more of the basic integration rules. These come from our basic differentiation rules, just kind of getting all of them real quick here. We already know that if you differentiate the natural log, you get 1 over x. So you're going to have to be able to integrate 1 over x back to natural log. So that's one of them. Our favorite is that if you differentiate e to the x, you get e to the x. So that's also probably going to be our favorite integral because it's the only function whose derivative and integral is the same thing as itself, the only one. These ones are harder for us to remember, so we're going to have to pay extra attention to them. We probably don't have arc sine, arc secant, and arc tan memorized, but arc sine's derivative was 1 over the square root of 1 minus x squared. So if I see something of that pattern, I gotta think, ooh, arc trig, and go to the arc trigs for these. Now, if you remember, we did do arc trigs for all 6 of them. So you don't see arc cosine listed here and arc cotan and arc cosecant. There is a reason for that. Let me pull up our table real quick. If you remember, the derivative of arc sine and arc cosine were the same thing. It's just one was positive and one was negative. But since a negative is is a constant multiple, it doesn't really need to be there. And so these things are going to be just the same. They're going to integrate the same way. And we're just going to use arc sine, the positive. And if it happens to have a negative one on top, keep it as a negative arc sine. And then by identities, if you really needed to be in terms of cosine, you can get there with identities. So, and cofunction angles. So we are not going to integrate things into the other 3. They're going to integrate into the positive 3. So, interesting fact. Okay, now in the back of the book, which is on my math lab, if you haven't seen it, you can get to these, or you can click on this link or type in this link to get to these. There is a collection of over 100 indefinite integrals that we can use just like these tables. We can integrate by tables. Now, some of those can also be done by other methods, but the common ones we want to focus on. So we have like 16 or so common ones, and we'll build a few more of those as we continue the section, but there are more of them if you need them to look up those tables. And I have seen some Calc 2 students, again, referring to those tables, and they have a section on making sure that they can make use of those tables as well. So that is something that gets focused on a little bit more in Calc 2, but just to keep in mind, there are hundreds of these. For differentiation, we got all the rules in like 20 or so, but for integration, there's a lot more rules. It's always harder to undo something than it is to do it. So in any of the mathematical operations, multiplication, division, division's the harder one, or exponentials and logarithms are the harder one. Same with integration. Okay, so let's take a look at some of the ones here on the bottom. I want to integrate 7e to the x. Love it because the integral of 7, constant multiple, gets left alone, and then I have e to the x, which integrates into e to the x itself. Throw on a plus c. Okay, now remember that we could not integrate power -1 using the power rule because that would have added to 0 if you added 1 to it, and you can't divide by 0. Instead, it's going to integrate to natural log. I told you I was going to get to that. That's how this one integrates. And so I want to first rewrite this one as 2 times 1 over x dx. And now I can more easily recognize that that integrates into 2 natural log of x dx. Plus c. Now it does officially integrate in 2 times the natural log of the absolute value of x. Most of the time we're lazy and we don't write the absolute value signs, even though we know that the natural log function can only accept positives. So they do technically need to be there because if you just have a 1 over x function, negatives can be plugged into that, and negatives cannot be plugged into the output, and the domain of a derivative can be no longer than the domain of the original. So if we're saying this is the original, then they had to have the absolute value. So they technically need to be there, but we're often lazy and don't write them. So if I don't write them, it's because, not because they don't need to be there on the natural log function, it's because conventionally humans are lazy. So they're there. Okay, now this one, it is a quotient with a sum in the denominator. If I have a 2-term denominator, I can't get that simplified. Luckily, I've got arc trig functions that allow me to find the antiderivative. Now, this doesn't quite match, but it's almost perfect. I need to get rid of the 3, but it's a constant multiple. So I'm going to rewrite that as 3 times the integral. And it doesn't matter if I have s squared plus 1 or 1 plus s squared, but if it makes us happy, we can switch the order to match because addition is commutative. And so I am integrating now 3 times 1 over 1 plus s squared ds, matches up exactly with the arctan integral. So we just get 3 times the arctan of s plus c. And again, if you are more used to writing arctan in the little -1 notation, of course that's the same function. Some people prefer writing out the arc, some people prefer writing it with the little -1. I like writing the arcs myself, but if you were not familiar with that notation, then that's fine. Either one. Okay, and then our next one, this looks most similar to number 16. I've got a couple extra numbers, but they're really just constant multiples, a multiple of 4 on the top and a multiple of 3 on the bottom. So I can pull out 4/3. This is 4/3 times 1 over y square root of y squared minus 1 dy. Now that looks exactly like something that's going to integrate into arc secant. It's just going to be 4/3 times arc secant of y plus c, and again, same deal on that one. The arcsecant's got to have a positive input. Normally we are lazy with those absolute value bars there as well.